Hello guys, welcome to my YouTube channel Banthiya Training and Consultancy. We are looking at mole concept and stoichiometry, and this subsection is basic concept of mole concept and Avogadro's number. This is lecture number 1 and I am Shreyans Banthiya. If you haven't seen Gay-Lussac's law, so please find the playlist above and get back to this video later on so that you can get a better clarity about mole concept and Avogadro's number. Let's start. Before we begin, let's understand what's atoms and molecules. Amedeo Avogardo in 1811 termed these concepts. He defined atoms as atom is the smallest particle of an element that can take part in a chemical reaction and may or may not be capable of independent existence. Couple of examples might be neon, helium, krypton. These are all inert gases and they are capable of independent existence. But whereas other elements are incapable of independent existence and for the stability they undergo reaction. Molecule is the smallest particle of an element or compound that can exist by itself. That is, it is stable in its original form. The number of atoms in a molecule is called its atomicity. For example, in H2 there are 2 atoms of hydrogen and hence its atomicity is 2. And we all know the basic structure, atomic structure of atom. Here there is protons, there is neutrons, electrons and nucleus. Nucleus is basically the address where protons and neutrons exist, whereas electrons revolve around the nucleus. And we should already know this. So Avogadro's law. Under the same conditions of temperature and pressure, equal volume of all gases contain the same number of molecules. Which means that if we assume that 1 liter of oxygen gas contain n molecules of the gas, then by Avogadro's law, under the same condition of temperature and pressure, 1 liter of hydrogen will also contain n molecules of hydrogen, 1 liter of nitrogen will contain n molecules of nitrogen. Now when we generalize, we can say that 1 liter of any gas will contain n molecules of that gas. And this is what Avogadro's proposed. So basically, when we see at this reaction, that is O2 plus 2H2 gives 2H2O. Let's assume that 1 volume of oxygen plus 2 volumes of hydrogen will give 2 volumes of H2O. And these volumes can be converted into molecules. So 50 molecules of oxygen will react with 100 molecules of hydrogen to give 100 molecules of water. This is what Avogadro stated. So basically, if volumes are same, then number of molecules will be same under the same condition of temperature and pressure, be it any gas, that is oxygen, nitrogen and methane is the example taken here. So let's take an example and understand if we have understood this concept clearly. A pharma industry manufactures a medicinal drug comprising of nitric oxide, that is NO, used as an energy booster. NO is produced by a reaction involving oxidation of ammonia. So under similar conditions of temperature and pressure, which species had the greatest number of molecules? So we have been asked the greatest number of molecules under the same conditions of temperature and pressure. So this is basically, according to the Gay-Lussac's law, we can write that 4:5:4 and H2O is liquid, so not applicable. Here we can easily see that oxygen has more number of molecules as the same amount of any gas contains the equal number of molecules. 4 parts, 5 parts and 4 parts. So obviously oxygen will be more. Let's understand the structure of hydrogen. And as hydrogen is the lightest element, that's very important. Hydrogen contains only 1 proton and 1 electron in its atom. And mass of 1 proton, we already know it is 1.67 into 10 raised to minus 27 kg. Mass of 1 hydrogen atom will automatically become 1.67 into 10 raised to minus 27 kgs because the mass of electron is negligible, as we have seen in the atomic structure chapter. Mass of 1 hydrogen atom is termed to be 1 atomic mass unit, that is AMU. And as per the latest IUPAC, that is International Union of Pure and Applied Chemistry, they have also given that U can be used as a nomenclature for atomic mass unit, which means unified unit, which they have termed as unified unit. So guys, keep this in mind. You can also use this. Now, relative atomic mass or atomic weight. This term was first given by John Dalton, who compared various weights of different atoms with hydrogen atom. And what he found was hydrogen, if considered to be 1 AMU, oxygen became 16, H2O will obviously become 18, and carbon was observed to be 12. But later on, it was observed that hydrogen was unable to react with all the elements known at that point of time. A better option, that is carbon 12 isotope, was considered to compare. The standard for comparison of mass of other atoms or molecules since 1961 was carbon 12. As hydrogen doesn't react with most of the elements and carbon does, it becomes easier to compare weight of carbon than hydrogen. And as we already know, mass of carbon 12 is 12 atomic mass units. So relative atomic mass, that is RAM, is the short form of relative atomic mass. So relative atomic mass is equal to mass of one atom of the element divided by mass of one carbon 12 isotope. Hydrogen would be 1 by 12, carbon would be 1, nitrogen would be 14 by 12, oxygen would be 16 by 12, sodium would be 23 by 12, and aluminium would be 27 by 12, which will be very difficult for us to calculate and work with. And hence what we did is, in the formula we just did a very small change, that is mass of one atom of the element divided by 1/12 of the mass of one carbon 12 atom, which becomes 1, and hence the denominator becomes 1, and it becomes easier for us to calculate. So now hydrogen's relative atomic mass becomes 1, carbons become 12, nitrogen 14, oxygen 16, sodium 23, and aluminum 27. Relative atomic mass, that is atomic weight, or it is also termed as RAM, is the number of times one atom of an element is heavier than 1/12 the mass of an atom of carbon 12, and we have already seen this formula. Now, does atomic mass of each and every element is a whole number? So no, we already know this. And why is that? Let's see with an example of chlorine isotope in nature. Natural elements are mixed of 2 or more isotopes of constant composition. That is, the number of atoms of each type of isotope in nature is fixed. For example, chlorine 35 has mass 35 and chlorine 37 has mass 37, and the relative abundance is 3:1. That is, chlorine 35 is 3 parts and chlorine 37 is 1 part. And by taking the weighted average, we come down to 35.5 AMU, and hence in the periodic table we can find the atomic weight of chlorine is 35.5. So mass number and relative atomic mass. Mass number basically that we have already studied is the total number of protons and neutrons of a particular atom, and which is supposed to be a whole number each and every time. But relative atomic mass is the average of the atomic masses of all the isotopes taking into account their relative abundance, and hence this is a weighted average, and hence the term comes relative atomic mass. I hope guys that you have understood it. Now, relative molecular mass or molecular weight, it is also termed as RMM. It is similar to relative atomic mass. Molecular weight of an element or compound is the number of times one molecule of the substance is heavier than 1/12 the mass of an atom of carbon 12. Directly, relative molecular mass gets the formula equals to mass of one atom of that element divided by 1/12 mass of the carbon 12 isotope. Let's see if we have understood this concept and solve this numerical. The relative molecular mass of NH3, given that the relative atomic masses of nitrogen is 14, hydrogen is 1, then NH3 will become 14 plus 3 times 1 divided by 1/12 into 12, which will come out to be 14 plus 3 equals to 17, and hence the relative molecular mass of ammonia is 17. The relative molecular mass of NH4 twice SO4, given that the relative atomic masses of nitrogen is 14, hydrogen is 1, sulfur is 32, oxygen is 16, is again the same method. NH4 twice SO4 will give 14 plus 4 into 1 whole bracket twice plus 32 plus 16 into 4 divided by 1/12 into atomic weight of carbon 12 isotope. So this will come down to 18 into 2 plus 32 plus 64 divided by 1, and this will be 36 plus 64 plus 32, which will finally give you 64 plus 36 will be 100. So 132 is your desired relative molecular mass of the given compound. Gram atomic mass, that is gram atom, and gram molecular mass, that is gram molecule. Gram atomic mass is the relative atomic mass of an element expressed in grams, basically representing the atomic masses in terms of grams is gram atomic mass, and similarly expressing the molecular mass of any given molecular compound in terms of grams is gram molecular mass. For an example, aluminium's relative atomic mass is 26.98, which is approximately 27. When we write it in grams, it becomes 27 grams, and so on. For example, carbon dioxide is 44 and it becomes gram molecule 44 grams. Mass of one atom of hydrogen is 1.67 into 10 raised to minus 27 kg, and we have already seen that. Mass of one atom of hydrogen is 1.67 into 10 raised to minus 24 grams. So basically what we have done is expressing kg into grams here. Now we know that weight of one atom is 1.67 into 10 raised to minus 24 grams. If I ask you what would be the number of atoms in 1 gram of hydrogen, then obviously you will cross multiply and you will get 6.02 into 10 raised to 23 atoms. Similarly, when we do the same procedure for sodium, it becomes again 6.023 into 10 raised to 23 atoms in 23 grams of sodium, and again with carbon, basically 6.02 into 10 raised to 23 atoms is termed as mole. What is mole? Mole is a term used to count the number of atoms in the given quantity. Atoms are very small, and hence we need a very large number to represent them, and counting them and calculating them would be a very tedious job, because in 1 gram of hydrogen there would be 602 sextillion atoms of hydrogen. To represent it in easy way, we have termed mole. Mole is a basic unit of atom of substance or a number just as dozen, pounds or pair. Mole in Latin means heap or pile, and here 1 mole of a gas equals to 6.02 into 10 raised to 23 atoms. Avogadro's number of atoms present in 12 grams of carbon 12 isotope is basically termed as Avogadro's number. In the acronym form, it can be written as Na or L. It is the number of atoms or molecules or ions present in 1 mole of a substance. 1 mole of oxygen atom contains 6.023 into 10 raised to 23. 1 mole of oxygen molecule will also contain 6.023 into 10 raised to 23 molecules. So Avogadro's number is 6.02 into 10 raised to 23. Molar volume is the volume which contains 1 mole of the particular substance at STP. So 1 mole occupies 22.4 liters or dm cube at STP, where we have already seen STP where temperature is 0 degrees Celsius, that is 273 Kelvin, and pressure is 760 mm of Hg or 76 centimeter Hg or 1 atmosphere. This is the entire summary of whatever we have seen in this session. Mole to Avogadro number and Avogadro number to the molecular mass or atomic mass. The entire relationship that we have studied. So 1 mole of oxygen atom will contain 6.02 into 10 raised to 23 atoms of oxygen, which will be equivalent to 16 grams of that particular atom. Similarly, 1 mole of oxygen molecule, that is O2, will contain again 6.02 into 10 raised to 23 molecules of oxygen, and which will have gram molecular mass as 32 grams. So this is a very important table for you to understand. In case you have any doubt, please comment in the comment section below. Thank you for watching this video. Please share, subscribe and like our channel, and please don't forget to press the bell icon if you don't want to miss any updates from our channel. Thank you.